All right, yes, it is my pleasure to introduce the second speaker of today's session, Rylee Lyman, talking about exploring the spine of outer space for free products.
Great. Thank you for the invitation and the opportunity to speak. So I guess in keeping with the theme of today, I'm going to tell you about a project that started out as a bit of a side quest. I'll tell you what the sort of the main quest or the goal theorem that I'm working towards is a little bit later on. But it turned out I need like this was sort of supposed to be the beginning sections of a paper, and then it ended up blowing up so much that I figured it could stand on its own. So that's I don't know, a little bit of the backstory of what's going on here. So I'm going to tell you about the spine of outer space for free products today. And I'm going to sort of, the exploring is we're going to learn how to move around in it and learn kind of the combinatorics of the spine. That's kind of the goal for today. So the story really begins with Culler and Vogtmann in the 80s. They defined a space called, now it's called outer space, for the outer automorphism group of a free group to act on. And I'm not really going to tell you much about Culler-Vogtmann outer space, except that wherever I say graph of groups, I'm going to say graph of groups in a bit. Wherever I say that, if you want to just think graph, then you'll be thinking of Culler-Vogtmann outer space. So I want to give an account of the spine of now Guirardel and Levitt outer space, which was defined in 2007 for a free product. So the setting is we have G, it's a countable group. And we're going to write it as a free product in kind of a specific form. So they're going to be finitely many, so finitely many n, in fact, groups AI. And G is going to be the free product of these groups. They're just countable groups. They don't have to be finitely generated or anything. And a free group of rank K. So this is kind of the setting. G can be kind of a wild group as long as it's countable. We just want to be able to write it as kind of a finitary free product. That's what's going on here. Great. I'm going to, this is just sort of a little bit of notation that I'm going to be using. The scripty A is supposed to be the set of conjugacy classes of the AI. So it's good. It's a little bit of, I don't know, notation that we're going to be holding on to. And some examples of countable groups that split as free products in this way are finitely generated groups. So if G is a finitely generated group, it has a Grushko decomposition, where each of these AI are what's called freely indecomposable, so you can't write them as a free product. And they're not infinite cyclic, because you throw all of the infinite cyclic groups over here by themselves in this free factor part. But that's not the only case of interest. In fact, a really interesting case is also where G is itself a free group and the A are free factors of G. This is what allows you to study automorphisms of free groups sort of inductively. This is sort of the right, I don't know, setting for induction. So that's our setting. And outer space is going to be built out of trees is one way of thinking about it. So let me tell you about the kind of trees that we're going to think about. Okay, so I wrote it, the thing from the previous slide. I'm going to be holding on to this bit of notation basically for the rest of the talk. So I'm fixing N and I'm fixing K. That's what's going on. So a Grushko G scripty A tree it's a simplicial tree. It's equipped with a G action with trivial edge stabilizers. And the elliptic subgroups, so the subgroups fixing a point, are all conjugate to subgroups of the AI. So that basically tells you everything you need to know about the action. If there were no AI, what this would be saying is that we have a group, a free group acting freely on a simplicial tree. That's what's going on. And this condition here, this elliptic subgroup, so we're basically saying these guys fix points of the tree, but nothing larger does. So the A, I, and their conjugates are all of our sort of maximal point stabilizers. And I'm going to say that two Grushko GA trees, T and T prime, are equivalent if there's a G equivariant homeomorphism between them. So one thing that this allows me to do is it allows me to kind of sweep the simplicial structure under the rug a little bit. Like you could imagine equivariantly subdividing an edge into a bajillion edges by just adding a lot of vertices. And this equivalence condition is saying I can just ignore that. Great. And so the spine of Guirardel-Levitt outer space, I'm going to call it K. And implicitly, it depends on both on G, the group, and A, this sort of what's allowed to be elliptic sort of bit of data. So the spine K of outer space, vertices are given by certain equivalence classes of Grishko-GA trees. And I'll tell you about what's up with the certain in a second. Okay, great. So that was trees. Now we're going to talk about graphs of groups, and I'm going to be thinking about graphs of groups basically for the rest of the talk. So the idea is that associated to a Grishko-GA tree, there's a quotient graph of groups, G. If you've never seen graph of groups before, I guess I just want to apologize because I won't be telling you sort of in detail what they are. But really all it is it's a gadget that keeps track of an action of a group on a tree. So you have a graph that's quite literally the quotient of the tree by the group action. And then there are some groups associated to it that are sort of keeping track of the stabilizer information. And then there's a so-called fundamental group of the graph of groups, and that ends up just being the group G that you started with. So our graph of groups, script DG, comes equipped with a marking. So what that is it's an isomorphism from our fixed group G to the fundamental group of this graph of groups. And this isomorphism is well-defined up to inner automorphism. Basically, because I don't want to pick up base points in my graph of groups, I just want to let that sort of move around. That should be fine with me. Great. So what I'm going to tell you now is some bits of like the properties, I guess, of our graph of groups they basically follow just immediately from our assumption that we have a Grishko-GA tree and we're taking the quotient. So the first is that our graph of groups is a finite graph and its first Betty number is K. So the rank of its fundamental group as an ordinary graph is K. So we're really seeing our free group of rank K kind of showing up here. There exist exactly n non-trivial vertex groups, which I'm going to call cone points, just so I don't have to say vertex with non-trivial vertex group, one for each of the AI. So each AI is showing up as one of my cone points, and that's all of the vertices with non-trivial vertex group. So all of the other vertex groups and all of my edge groups are trivial. And so those are my sort of given for free. This next one, I can assume because I am allowed to kind of vary the simplicial structure on my tree at will, is that all valence 1 and all valence 2 vertices of my graph G are cone points. This is kind of nice. It turns out because it bounds what will be the dimension of our outer space, basically by a kind of Euler characteristic or union that I think I won't give, but it's cute. And then this final condition is not actually a consequence of having a Grishko-GA tree, but what it amounts to is I'm shrinking my complex K by an equivariant deformation retraction. So this kind of technical condition says that if removing an open edge of my graph G would disconnect it into two components, then both complementary components have to contain a cone point. So I'm allowed certain separating edges in my graph, but only certain ones. Other separating edges, I'm just gonna forget about. Great, okay, so those are our properties. This was a bit of a mouthful. Let me give you some examples. Okay, so here, let me have my group G be the free product of 3 groups, A1, A2, A3. I don't really care what they are, and a free group of rank 2. This first one, this first graph of groups is kind of special. It's called a thistle. So the properties that it has that make it special is it has one vertex which is not a cone point, right here. And all of the other edges are kind of involved with that vertex. So I have some edges that form loops. I have 2 of them because I have a free group of rank 2. And then my other edges connect to the cone points of my graph of groups. So this is a thistle. It has 3 prickles and 2 petals. If I collapse an edge of my thistle, so maybe this edge right here, I get what I'm going to call a bug. A bug looks a lot like a thistle, except for instead of having this center vertex that's not a cone point, it is a cone point. Oops, let me now erase that. So I have this vertex here, which is a cone point, A1, and then the arrangement of everything else is kind of like a thistle. So the condition 5 on that previous slide was about separating edges of my graph of groups. This separating edge is fine. Why is it fine? Because the complement contains 2 cone points. So is this one. And actually also this separating edge is fine because the complement contains, or both complementary components contain a cone point. This separating edge right here is not fine because this component over here contains no cone point. So this guy is not allowed to be part of my spine of outer space. Great. So those are my examples. Let me continue telling about sort of the conditions on the graph of groups. So this last one, I guess I also want to apologize slightly for. So vertices of the spine should be equivalence classes of marked graphs of groups. And so I have to tell you a little bit about what is the notion of equivalence that I'm allowed. And it's a little technical, but it's not so bad. So what it is that there should be an isomorphism of graphs of groups here. So whatever that is, I'll tell you in a second. And it should make this triangle here of group homomorphisms commute up to inner automorphism. Remember, my marking isomorphisms were well defined up to inner automorphism, I guess. So this guy should only be allowed to make the triangle commute up to inner automorphism. If you know a little bit about mapping class groups, or I guess rather Teichmüller space, and you've seen markings of surfaces, this is exactly the same sort of thing. This is supposed to be kind of your isometry of hyperbolic surfaces, if you will. Okay, great. So that's my notion of equivalence. It won't come up, so don't worry about it too much. Or I guess it will come up. That's why I put it on the slides. Sorry. So that's great. I can also tell you what simplices, higher simplices of my spine of outer space are. They're chains of forest collapses. So just like on the previous slide, I had a collapse of an edge from a thistle to a bud. That would be an edge of the spine of outer space. There's a little bit of a technicality. I can't allow 2 different cone points to collide when I collapse a forest. So only certain forests are allowed to be collapsible, but that's not neither here nor there for us. Okay, great. So I'm going to actually tell you what an isomorphism of graphs of groups are, because it will come up. So what it is it's a graph isomorphism. So that's not so bad. And then we have isomorphisms of our vertex groups. So H sub V goes from my vertex group for V to the vertex group of its image. So it should be an isomorphism because I want H to be an isomorphism. And then the kind of funky bit of the definition is this bit right here. What it says is for every oriented edge of my graph of groups, I'm allowed a little twisty element is how you should think of them. And what it is it's an element of the vertex group in the target. So I've taken the image of the terminal vertex of my oriented edge. That's what this tau is saying. So here's this is not important, but just for like clarity, what really is this map H sharp on like the fundamental group? Well, if I have an edge path in my graph of groups, remember what that is it's an edge, a sequence of edges that form a path in my graph. So that's my E1 up to EK. And then every time I hit a vertex, I can pick up an element of the vertex group. So I get a G1, a G2, etc. And the way that H acts is it acts as the isomorphism on vertex groups on my vertex group elements. Great. It acts as the graph isomorphism on my edges. Great. And then it also twists my edges by these little delta E's. So that's the sort of twisting that's going on. Great. That's that. Yeah, thank you for putting up with me telling you a little bit of the more technical bits of this tiny subfield. Great, so that's outer space. My vertices are equivalence classes of marked graphs of groups. My K simplices are chains of forest collapses. Awesome. Let me tell you, I believe, about my results. So the results, so these are in progress. The main theorem is that the spine is contractible. As a corollary, I recover a theorem of Guirardel and Levitt from 2007 that the full outer space, I've only told you what the spine is, but you should think of the full outer space as like sort of recording metric structures on your graph of groups. The full outer space is contractible in what's called the weak topology. Whoops. There are several topologies, 3 on outer space. 2 of them are really the same, but they have slightly different fields. And then the weak topology is kind of the odd one out. The reason we only get contractibility in the weak topology, which is kind of odd, right, is that the spine is not actually an equivariant deformation retraction of the outer space in the axes topology, which is sort of the usual topology. The reason being that this is a locally infinite simplicial complex, so you can have lots of sequences of points in your simplicial complex that don't have a convergent subsequence, but they do in what's called the axes topology. So it's really just a question of the topology mismatch of what's going on that comes up when you have this locally infinite nonsense, really. This is a theme of many of my projects is grappling with locally infinite simplicial complexes and how weird their topology is. Okay, so this is the main theorem of what sort of grew out of my side quest. The original goal is to study the connectivity of K at infinity when K is locally finite. So what that means, or when that happens, is when all of my groups AI are finite groups. This is sort of related to the question, so I'll write it. So related to if out of my free product, oh, let me just write G, sorry. G is a virtual duality group. One of the ways of showing that a group is a virtual duality group in the sense of theory Ekman is to argue that it is sufficiently connected at infinity. So this would be sort of a first step towards that goal. Yeah, and as I say, like I needed a bunch of properties of K to start talking about this sort of thing. And I eventually needed so many properties that I was like, well, I might as well just show that it's contractible. Oh, before I forget, I also want to point out that the corollary implies the theorem. Because if you're a deformation retraction of a contractible space, then you're contractible. So this is the point of the theorem is really that this is a new proof. And a sort of more direct combinatorial proof than the proof that's given by Guirardel and Levitt. Great, awesome. Oh, good, and I'm doing great on time too. Great. So let me tell you the strategy of the proof. So the strategy of the proof is the idea essentially goes back to Culler and Vogtmann's original proof showing that outer space for a free group is contractible. What they do is they define a norm on thistles, or well, for them it's roses. For us it's thistles. The norm, so let theta be a thistle. The norm of theta is going to be the sum over some finite collection W of conjugacy classes of the hyperbolic length of gamma in the tree action determined by theta. Or if you want to think of the graph of groups, you can realize gamma as a like a loop that doesn't backtrack in a graph of group sense. And then you just count the number of edges in that loop. So that's what's going on here. That's the norm on my thistle. And I want to think of it like a Morse function on my complex. And then I want to show that using the properties of the norm, I want to show that the complex K deformation retracts to a subspace where the norm is minimized. And then for a clever choice of norm, this should be something like very small that we understand. So the goal here would be that the minimum subspace, so came in for a clever choice of W, should be maybe just like the star, hopefully, of a specific thistle. So since it's a star, you know that it's contractible. So therefore the whole complex is contractible because it deformation retracts onto this contractible subspace. Great, so that's the strategy of the proof. I want to tell you kind of the monster that I'm grappling with in the next couple of weeks, keeping with our theme. The difficulty is that roses in Culler Vogtmann's outer space. So what is a rose? A rose is just a graph that looks like this. So here's a rose with, I don't know, 4 petals. So it has one vertex. All of the edges form loops at the vertex. Roses are, so you can think of defining like a poset of graphs based on the number of like vertices and like the, what is this? The relations of my poset would be collapsing onto each other or expanding, I guess, if you, I don't know, what amounts to reversing the order. Roses are minimal in that poset is the point, and that's very helpful in Culler-Vogtmann outer space. But it's just not true that thistles are minimal, nor is it true that everything either collapses or expands to a thistle. There are just silly things that you can do, like, for example, let me draw something that doesn't collapse or expand to a thistle. So it looks like this. So if you just put one of your vertex groups on the wrong side of another one, you're hosed. This guy does not collapse nor expand to a thistle. So this makes the Morse theory argument more complicated, basically because you have to deal with these guys specially. As I wrote this slide, I was like, okay, so what you do is you just account for them in the argument. So rather than just focusing on thistles, maybe you focus on like generalized thistles, which look something like this, but could look maybe a little bit less nice. So that I don't know. That's I guess this is the real piece of the argument that will make it more than just an exercise in generalization. Great. So in my last minute or so, let me just tell you a key way of moving around the complex. And so they're called Whitehead moves. And understanding the combinatorics of Whitehead moves is basically the key in the Morse theory argument. So there are 2 kinds. There are expand Whitehead moves. So we're starting at a thistle here, And what I'm going to do is I'm going to blow up something I'm going to call an ideal edge. So here it is, the ideal edge. And what it gives me is a new graph of groups with 2 free vertices, 2 vertices that are not cone points. And then if I change my my marking on my thistle now, or sorry, on my not thistle, I now have a new unlabeled edge, and I'm just going to collapse it and get the thistle that I get by collapsing it. So these are the same graph of groups, just the marking is slightly different. And as you can see, what it amounts to doing is it changes on the thistle level my marking by some automorphism of my free product. And the automorphism that you get is sort of determined by the combinatorics of whether the edge is oriented this way, or maybe the edge is completely on the wrong side of the new edge, or maybe it's completely on the right side. That's kind of what's going on. So the Whitehead moves correspond to Whitehead automorphisms of free products. That's the punchline. And then the other one is called a collapse Whitehead move. And what it is you collapse from a thistle to a bug. So that's what's going on here. You twist by an automorphism of your graph of groups. That's why I told you what that was. So this automorphism twists these oriented edges by the same element A. Doesn't have to be the same element, but just for the illustration purposes. So these are the same graph of groups, but now when I expand A back out, I get something new that was different. So that's the collapse Whitehead move. Great, so I'll stop there.
Great, let's thank Rylee. Are there any questions for the speaker? Okay, if there's no more questions, then let's thank Rylee again. Thank you, Rylee.
Thank you
That was
for
really
the
nice.
attention.